This video is brought to you by mywayteaching.com.
In this part, let us study about dimensions. What is this dimension and how to get this dimensional formula? Let's see. Any physical quantity can be expressed in terms of some combination of seven fundamental or base quantities, isn't it? Yes. For convenience, the base quantities are represented by a letter symbol. Generally, we will represent mass by a letter M. Okay, and we'll represent length by the letter L, and we will represent time by the letter T, and we'll represent electric current by A. So the thermodynamic temperature, the amount of substance, and the luminous intensity are denoted by the symbols like K. Temperature, amount of substance is represented by symbol mole, and the intensity is represented by CD, respectively. When a physical quantity is expressed with appropriate powers of this M, L, T, A, and even this K, mole, and CD, then such an expression for physical quantity is called the dimensional formula. Okay, when a physical quantity is expressed with in terms of powers of mass, okay, when it is expressed with appropriate powers of mass, length, time, current, and temperature, mole, and intensity, we will call it as dimensional formula. The power or exponents of M, L, T are called as dimensions. Okay, we will represent like this, right? The dimensions 1, 2, 3. So these powers are called as dimensions. The dimensional formula of physical quantity is usually expressed in turn square brackets along with the symbol of a physical quantity. For example, I will give the example of velocity. If I want to express the dimensional formula for this velocity, then we should write the base quantities, that is displacement by time, isn't it? Velocity is displacement by time, and this displacement is nothing but L. So to the power 1, and for the time the symbol is time T and to the power 1. So the dimensional formula for this is given by, for velocity, the dimensional formula is given by m raised to 0, L raised to 1, and T raised to minus 1. Got this? So this is the dimensional formula. So let us consider one more example. For example, dimension of kinetic energy. Kinetic energy is given by half into mass into velocity square. So the dimensional formula for this kinetic energy, this constant is having no dimension, so we should neglect it, and we should consider dimensional formula for this mass as well as for this velocity. And for mass, we'll write it like this with a symbol m, isn't it? And for velocity, just now we derived the dimensional formula, that is given by m We already derived it for V, isn't it? It is m raised to 0, L raised to 1 and T raised to minus 1 whole square. And finally, the dimensional formula for kinetic energy is given by m raised to 1, L raised to 2 and T raised to minus 2. Now you got the idea of dimensions, isn't it? Yes, dimensions are nothing but it is just an expression for physical quantity, okay, which is expressed with appropriate powers of m, l, t, k, a, etc. Now let us study the next part. So the dimensional formula is nothing but the dimensional formula of a physical quantity is the formula which tells us how and which of the fundamental units have been used for the measurement of that quantity. So we can consider as a similar example like velocity is given by displacement by time. So the dimensional formula, it tells which are the quantities are used for the measurement of velocity. It is distance and time, isn't it? And we can write the appropriate dimensions for that. For time, it is t raised to 1, and the dimensional formula for velocity is m raised to 0, L raised to 1 and t raised to minus 1. Now let us see how to write dimensions of physical quantity. So there will be some things that we should consider while writing the dimensions of a physical quantity. What are those? Let us see. Write the formula for that quantity with the quantity on LHS of the equation. Okay. First, we should write the quantity formula for that quantity with the quantity on LHS of the equation. For example, if I say kinetic energy, then I should write the formula, isn't it? K is equal to half mv square. That is the first step. Convert all the quantities on RHS into the fundamental quantities like mass, length and time. So we know m is mass, so we'll convert it into fundamental quantity. That is, it belongs to length, isn't it? It belongs to the mass. The fundamental quantity itself is mass. Again, for velocity, we can write it using the fundamental quantities, that is displacement by time, isn't it? Substitute mass m, l and t for mass, length and time respectively. We know that as we considered in the previous example. Collect the terms of m, l, t and find the resultant powers which give the dimensions of the quantity in mass, length and time respectively. So I'll explain this using one simple example of velocity. So first step is writing the formula. So velocity is given by displacement by time. The next First is writing the formula. The next is convert all the quantities on RHS into the fundamental quantities like mass, length, time. So already these two are in the fundamental quantities, distance and time. No need of converting it again. Substitute m, l, t for mass, length and time respectively. So for distance we should substitute it as L raised to 1 and for time we should substitute it as L raised t raised to 1. And finally collect the terms of m, l, t. Here m does not have any role to play, so m will be 0 and L will be 1 and t will be minus 1. So here in the final stage we'll calculate the resultant powers which give the dimensions of the quantity in mass, length and time. So these are the steps involved in writing a dimensional quantity. Okay, dimensions for a quantity. Now let us study the characteristics of dimensions. The first characteristic is dimensions of a physical quantity are independent of the system of units. Okay, these dimensions does not depend on the system of units, or we can say SI system. Okay, that is the first characteristic. Quantities having similar dimensions can be added or subtracted from each other, which means we cannot add dimensions of velocity to the dimension of what? Yes, we cannot add dimensions of velocity to the dimensions of force. It is not possible. Quantities having similar dimensions can be added or subtracted from each other. That is the second point. And the third point is dimensions of a physical quantity can be obtained from its units and vice versa. Isn't it? We can obtain the dimensions using its units. In case of velocity, I wrote it, the formula we wrote it like displacement by time. So the unit of distance is length, so we'll use L. The unit of time is second, so we write T. So using the units of these fundamental quantities, we are going to get the dimensions for the physical quantity. Two different physical quantities may have same dimensions. It's not like that. These dimensions should be unique. Even any two physical quantities, they may have same dimensions. That's not a problem. Multiplication division of dimensions of two physical quantities results in productions of dimensions of a third quantity. Okay, if you multiply or divide any two dimensions or in dimensions of two physical quantity, then the result whatever we'll get, that will be the dimension for a third quantity, isn't it? Again, I'll give the similar example of this velocity. Here displacement and time, the dimension for displacement and is divided with the dimension of time, and that will give the dimension for velocity, isn't it? So after this only we will get the dimension for velocity. So multiplication or division of dimensions of two physical quantities results in production of dimensions of a third quantity. Now let us see what is this dimensional analysis is. The method of obtaining the solutions to some several problems in physics by using the formula is called as dimensional analysis. Then what is the use of this dimensional analysis then? Yes, it is used to obtain the relation between two units. The first is it is used to obtain the relation between two units. So we can compare two system of units using these dimensions. Okay, that is possible using this dimension. And the second one is to check the dimensional consistency of an equation connecting different physical quantities. We can check whether the equation is dimensionally correct or not. And the third important point is to derive an equation for a physical quantity in terms of other physical quantity, isn't it? So we derive an equation for a physical quantity using dimensions of other physical quantity. As kinetic energy, will derive the dimensional value or the dimension for kinetic energy using the dimensions of mass as well as velocity. So this is also possible in case of dimensional analysis. Now let us see what is the principle of homogeneity. It states that the dimensional formulae of every term on the two sides of a correct relation must be same, which means whatever the dimension we get on the LHS of the equation must be same on the RHS also. It should be equal to the Let us consider the simple example to understand the homogeneity of dimensions, or we can say dimensional consistency. Okay. Let us consider an equation half mv square is equal to mgh, where m is the mass of the body, v its velocity, g is the acceleration due to gravity, and h is the height. Check whether this equation is dimensionally correct, or in other words, we can say check the homogeneity of equation. So the given equation is half into mv square is equal to mgh. Okay, and the dimensions on LHS side is given by, we know the LHS is half mv square, and the dimensions for this is given by, so half is a dimensionless quantity, and for mass we have m, and for velocity we have L into t raised to minus 1 whole square, and the resultant value will be m L square and t raised to minus 2. So this is the LHS side dimension. So if we consider RHS side, that is given by mgh, and again for m we have the dimension m, and for g the dimension is given by L square t raised to minus 2. Okay, and the final equation, that is given by m L square t raised to minus 2. So here the dimensions of LHS is equal to the dimensions of RHS, isn't it? So we can say these two equations are dimensionally correct. Homogeneity of equations is satisfied, isn't it? So this is what a homogeneity is.